All right, this is chapter 15, physics, lecture 2. And where the last video cut off was talking about an open switch and how that opened the circuit. And the next topic, we're on page 3 in your notes, series versus parallel circuits. So a series circuit, in order for current to flow, all devices must have connections. I'm going to draw one of those in a little bit. And if a circuit is wired in parallel, that means the resistors are wired in parallel, then the devices operate independently. Let me give you an example. If you have a string of Christmas tree lights, if they are wired in series, if one bulb goes out, they all go out. And that's the way they used to be wired, so it was a real pain to figure out which bulb was bad. If they're wired in parallel, which is the way they're wired now, if a bulb goes out, the rest of the bulbs will still operate. All right, so let's draw an example. So you have some space in your notes to draw. You can draw them side by side. Resistors in series. Okay, so let's say we have a circuit where the resistors are wired in series. I'm going to do 3 of them. Okay, so the current is going to flow out of the positive side and back into the negative side, and it's going to have to go through each one of these resistors. It doesn't have a choice. It's got to go through all of them to get back to the negative side of the battery. Okay, we'll call this one R1, R2, and R3. So to get the total resistance of this circuit, we call that the effective resistance. You just add up the 3 resistors, R1 plus R2 plus R3. So if I were to draw an equivalent circuit with just one resistor, we could draw a circuit with just a single resistor like that. And that would be our effective resistance. You would add those 3 up and you'd have a single resistor. This is called an equivalent circuit. Okay, if you want to pause the video, I'm going to erase. Yeah, let's take a look at resistors in parallel. Okay, to get the effective resistance for resistors wired in parallel, it's 1 over, excuse me, this, I need to redo that. Sorry about that. The formula is 1 over the effective resistance is equal to 1 over the first resistor plus 1 over the second resistor plus 1 over the third resistor. To however many resistors you have. So an example of a parallel circuit, I could draw this out, is they look, the way we draw them is they actually look geometrically parallel. Okay, so we could call, let's say this one R1, the second one R2, the third one R3. Okay, so our current, the current actually, you have 3 different currents here. One of them just goes through R1. We'll call that I1. And then one of them branches off. Each one of these sections is called a branch. That's I2. This would be I3. our voltage source down here. Okay, so our equivalent circuit, if I wanted to take all three of those resistors and just make it into one, that REFF, I would use this formula, but I'm going to show you an easier way to use put that formula in your calculator. REFF, instead of using all the fractions, all right, it's going to be R1 to the minus 1, because your calculator will have a minus 1 button, plus R2 to the minus 1, plus R3 to the minus 1, all to the minus 1 power. Okay, you put it in your calculator that way, and it's a lot easier than doing it as a fraction, although you can do it as fraction also in most calculators. Okay, if you want to pause the video, we will go work a couple problems. Okay, on your own 15.5, we're on the bottom of page 507. All right, so I'm going to just pull the book over into view. I hope you can see that. So 15.5, all right, we've got this circuit, and you can see geometrically that those resistors are wired in parallel. Okay, so what is the equivalent resistance, or the total resistance of that circuit? All right, so the effective resistance is going to be 111 to the minus 1 plus 222 to the minus 1 plus 333, the third resistor, to the minus 1, and you have to raise all of that to the minus 1 power. If you do that, you'll get 60.6 ohms. So go ahead and try that in your calculator. Make sure you can get that to work. Sometimes people forget to do the last step, to raise the entire parenthetical expression to the negative 1 power. All right, so that is the equivalent resistance of that circuit where all the resistors are wired in parallel. So let's look at 15.7. Okay, so I'm going to pull the book into view there. And you can see that these resistors, excuse me, this is 15.6, sorry about that. These resistors are wired in series. The current must go through all three. So we use our series resistance equation. So our effective resistance would be, we would just add the three resistors up. 111 plus 222 plus 333. And that is 666 ohms. So that's a scary circuit. Now let's say in the homework it asks you for the power. And let's say this particular circuit had a battery or a voltage source of 120 volts. So to get the power for this circuit, since we know voltage and we know resistance, let's use the V squared over R. All right, so the book doesn't ask you this. I'm just adding this as a homework aid. So we have 120 volts squared over 666 ohms. All right, and that will give you a power of 21.6 watts. So what you're capable of doing from a homework standpoint are the review questions. You can do 1 through 7. And the practice problems with these, with lecture 1 and lecture 2, you've got enough also to do 1 through 7. So give those a try, and we will pick up from there on the next lecture and hopefully finish out the chapter.